Alex, and it's New Year, which means time to test out my first ASIC that I designed. I'm going to go through the setup that I have, explain parts of it, explain parts of the ASIC that I designed, and then follow it up with the demo. So originally, I created this chip as part of a ELEC 422 final project, and it's going to emulate the game Whack-A-Mole. It's about 3,000 or 4,000 transistors, I believe, um, and it works, as you'll see soon. For a bit of background, the setup that I have here is I have a 5-volt rail set up because this is the 5-volt process half micron from Moses that fabricated it, as well as I have a function generator that's generating the clock input. I'm taking the input and running it in here, and then I'm running it through a series of NORs and NANDs in order to create a two-phase non-overlapping clock. It's pretty. You can't really do that with the regular function generator. So I decided to scrounge some parts to create that, and did so using this little circuit over here. We take the input, we invert it, and then we have it being fed into these parallel NOR gates where it's then buffered, and then the output is going into the other to ensure that there's always one signal up, one signal down, and they never overlap. So a couple of the other components on here. Up here, these first three LEDs are going to represent the states that are output from the chip. You're going to see a couple, mainly this one will be on generally whenever the game is over. This one will be on whenever it's expecting a button press, and then the other one will come on during startup. These LEDs represent the score. Right now, it's just in binary. One of the things that I'm going to do in the future is change the Verilog code that I used in order to create in order to have it output to a 7-segment display natively. Right here, this LED is used to say, okay, should we show the game board or not? Because in Whack-A-Mole, typically you have like 6 or 8 moles, and the pseudo-random number generator that's inside of there, it's a linear feedback shift register. It can have a certain state that it wants to output. However, this is used to say, okay, we know where the placement should be, but we don't want to show it for this one. And then right here is our start button. Whenever I hold this down and the clock is running, the things will light up and it'll start showing the states. It'll start showing the placement. These three LEDs are for the placement of the moles. In the actual implementation, they should be going to a decoder, which will then light up tactile LEDs so that you can hit them. And because obviously in the 0 case you can't really hit a 0 button, I've added one up here, which goes from the output of the OR gates to say, okay, yes, something has been pressed. Go through the next logic step. And so now I'm going to demo. Let's see, everything visible. Nope. Close enough. There we go. Alrighty, so now I'm going to just move this up. Bingo. Alright, so now I'm going to hit start. See, it's ready. Now I hit these. For the LFSR, there is a pre-programmed sequence, and so it's going to have that one for a few times, but that was the maximal period LFSR for just 7 bits. And as you can see, these are corresponding to different placements, and whenever I hit everything, it works, the score increases. Oops, hit the wrong one. Start over. Oops, how did I mess that up again? Bingo. Dun, dun, dun. See, and now I have to go up here. Bingo. Ooh, okay, so there, I messed up. And as you can see, I already used the start button again to show, okay, it does go into the next state. One of the things that I can do also is I can reset it back to its original state. Everything goes off and goes there, and then I start up again. Ta-da, and then it goes through the same sequence. And right now the clock is only going at I'd say 2 or 3 hertz, well, 1.6 hertz, and I'll turn it up to 10 kilohertz. Immediately goes there, but now, um, well, let's do 100. This is with the clock set to about 160 hertz. You can see that it goes through everything really quickly as I hold down the start button, just showing that it can handle those types of speeds. And now let's do megahertz. It's going through a lot of stuff. So one of the other things that I'm going to do in the future is increase the internal clock register, the internal counter, to handle going at, say, 32 megahertz. That way I won't have to source a two-phase clock. I can just have it go. I can just input a regular clock to the system and then create my own internal two-phase one, as well as creating a PCB, so that instead of having all these wires that I need to create, as well as the kind of jury-rigged, the finding different 7400 series circuits and random laps across campus during winter, it'll all just be there, which will be really nice. And yeah, so that's design verification of my first ASIC.